professor of neurology at Columbia University, the director of the critical care neurology. I have the pleasure of talking today about the EEG in consciousness disorders. These are my disclosures, my funding from federal agencies, including work on books, and I'm a minority shareholder of ICE Neurosystems. I have structured the talk to start talking about different aspects, how you can study the brain of an unconscious patient. So we encounter patients that have disorders of consciousness on a daily basis in the ICU. And I thought that I structure the talk around different approaches, how we could use the EEG to assess consciousness and then also to use it in prognostication. I will start out by looking at the brain at rest. This starts with some feature descriptions and computational analysis of the EEG. I will talk about brain perturbed tasks like passive tasks and active tasks. And I will sort of introduce to you what I'm talking about there along the talk. So let's think about first the brain at rest. This is the most easy sort of approach. You look at the EEG, the waveforms that you record, and you describe what you see. A good example of this is how EEG is used in cardiac arrest patients, even in the most recent guidelines that have been published by the European Society of Intensive Care Medicine. EEG features quite heavily in these guidelines. So as assessing a patient as having a poor outcome, there being likely a malignant EEG pattern, and I'll show you what that means. For example, a suppressed background activity or burst suppression within the first 24 hours and beyond, and status myoclonicus for within 72 hours and beyond, are considered to be patterns that are described on EEG, features seen on EEG that associate with outcomes. EEG reactivity, which basically means that the patient is stimulated and the EEG response is assessed, did not make it into the guidelines, even though there have been a number of studies describing this as having predictive power, but there's inconsistency associated with the stimulation and with the assessment of responsiveness. Be that as it may, you can think, for example, about EEGs that you may see in patients with cardiac arrest. This is an example of a malignant EEG pattern. You have a suppressed background or suppression burst, so you can see flat EEG here and bursts of activity. And there are patients with so-called identical bursts. So every burst looks about the same. Here on the left side, you can see that there's a number of different bursts in this patient, whereas here on the right side, you see that in patient A or patient B or patient C, each burst looks very similar. By in a number of papers by Van Putten and colleagues and Hofmeier, they describe this as a pattern seen mostly in patients with poor outcome. So that's one approach how you can describe EEG patterns. There's a number of other things. For example, here you can see status myoclonicus. Some patients have also patterns within that are more associated with worse outcome. So for example, this polyspike pattern described seen here on the left versus the continuous background activity with some sort of spike wave complexes has been identified by Jonathan Elmer in a paper as being more prognostic of outcome as well. When we think about these features that are just described, we have to remember that there is a danger of us just describing this and how can we extrapolate that to other settings. So there are efforts underway of standardizing both, not just the terminology, but also how this is assessed, for example, with quantitative EEG analysis, the responsiveness, and then also efforts underway standardizing the stimulus. One approach here was in a paper where we looked at this recently and looked at patients each time that they got a little finger prick when they were assessed for example, when glucose was measured, and then looked at the EEG response. And we found that could actually slightly improve the accuracy of predicting outcomes in patients with cardiac arrest. So this quantitative EEG analysis of a standardized response may in the future actually allow us to more accurately predict outcomes. What am I talking about when I say computational analysis? So when you take the raw EEG, this is just an example of a patient with EEG recorded here. You can analyze that in a number of ways. So you can do a fast Fourier transform, which basically breaks the EEG up into slow and faster frequencies and looks at the power in these frequency ranges. And then those features, this power in different frequency ranges can further be analyzed. So one, we can calculate power spectral density. Here is a spatial map of the amplitudes in these different spectra. Here you can see across different frequencies, slow frequencies here on the left, high frequencies on the right. You can see the power difference, or over time. This is on the right here. This little spectrogram shows that over time, over 30 minutes, you can see the color indicates the power. So you can display this in different ways. You can also look at the EEG signal, this digital EEG signal, in terms of functional connectivity. That means you look at how one waveform on one electrode correlates with another electrode on a different part of the brain. And that allows you to calculate coherence or weighted symbolic mutual information, and allows you to look at functional connectivity. Complexity is the last thing I just want to mention briefly, that looks at how complex the EEG signal is. You can imagine if somebody is completely flatline or has very uniform patterns, the complexity is very low. Whereas if somebody has, for example, a normal EEG, there's a very high degree of complexity. So that allows you to quantitate information in the EEG and look at, sort of correlate that with consciousness or with outcomes. Here is an example. This is a paper recently by Peter Forgash from Cornell, where he looked at patients that had different spectrograms. So this was where patients here were patients that remained in coma or died, and you can see that the spectrogram, again at the bottom on the x-axis is frequencies, on the y-axis is power, and you can see that actually the spectrogram of patients that died or had very poor outcome looks distinctly different to patients that on the right hand of this sort of curve here that have good outcomes and have recovery of consciousness. And this allows you then, as these patients transition through different states, actually to track quantitatively how patients recover consciousness, and then potentially use this also to predict outcomes. This was in cardiac arrest. Here I show you on the left side of the screen a cohort of patients where we looked at patients with acute subarachnoid hemorrhage, and on the left side the plots are summarizing conscious patients. On the right side are unconscious patients. You can see that the alpha power indicated by the higher color looks much more distinctly elevated in patients that are conscious compared to unconscious patients. The complexity of the EEG signal, here displayed as theta permutation entropy, is much higher in conscious compared to unconscious patients. In chronic patients with disorders of consciousness, mostly after TBI, interestingly enough, researchers from Paris found very similar plots. So you can see that the alpha power in the conscious patients, chronically conscious patients compared to the chronically unconscious patients after TBI, is much higher, whereas the theta permutation entropy is also higher in the conscious patients compared to the unconscious patients. So potentially we can generalize these EEG features across different brain injury etiologies and also across different acuities of brain injury. Again, coherence, functional connectivity can be analyzed. Here you can see a nice example. This is a patient cohort where patients got induced unconsciousness. These patients underwent anesthesia, and they were healthy, and they were conscious before, underwent anesthesia, induction of anesthesia, maintenance of anesthesia, reemergence of anesthesia, and then awake. And you can see that the alpha frequency coherence, so mid-frequency coherence, functional connectivity is located in the back of the brain while patients are conscious, locates to the front of the brain when patients are unconscious, and as they recover consciousness, goes to the back of the brain again. WSMI is another way of looking at functional connectivity, and you can see that different conscious states have very distinctly graded differences in this WSMI information. You can see that vegetative or unresponsive wakefulness state patients have a very, very low functional connectivity. MCS, minimally conscious state patients, have a slightly higher, whereas emergence patients or conscious patients have a much higher functional connectivity than the other patient states. Can we also use this in other ways, not just to assess a state of consciousness? So this was explored by the group in Paris, and they took a number of these EEG features, again, power features, complexity features, and connectivity measures, and they fed that. They took a big cohort of patients, and they took 80% of the data, and they fed that into a machine learning algorithm. The machine learning algorithm, this computer program, learned what was it in the EEG that was distinctly different between these different behavioral states. And then they took a part of the cohort that they did not use for the training and had it just analyze the EEG and say what the behavioral state would likely be based on the EEG. And so it classified patients into vegetative state or minimally conscious state. Interestingly, when you compared it, because you had the ground truth, patients were relatively accurately classified, except for those clinically in a vegetative state. So vegetative state means patients are not conscious. They cannot interact with the examiner. And a third of the patients where the computer program thought the patients were conscious, where when you went to the bedside and examined the patient, were actually not conscious. What was interesting about those patients, let's say, that were falsely classified as being conscious based on the EEG, but in clinical examination were not conscious, those were had a much higher chance to recover clinically in the next couple of weeks and months than those that were correctly classified. So in summary, basically the EEG detected something there already in these patients that you as an examiner at the bedside could not. So could it predict the future a little bit? So that's what they went on and did this in a much larger cohort. They actually fed this information into a much larger machine learning algorithm, classified patients, and developed an automatic classification way of classifying patients into conscious and unconscious patients. So this is work that's ongoing, but it's quite promising. Let me switch gears. So this was all the brain at rest. So let's see, can we look at the EEG or the electrical activity recorded from the brain when we disturb the system with something? So one way to do that is to play something over headphones to the patient. And the classic one that is used mostly in the psychology literature is the oddball paradigm, where you play tones to the patient. You go through like beep, 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 beep. And there's one that is out of sync. That is the oddball. And you record how the brain reacts to that. So the brain can actually reacts to that in a systematic way, and it generates a wave, a very delayed wave in the brain that you can sample out from the background of the EEG. That's called the P300. That's been associated with predicting outcomes. The Paris group took it a step further, and they actually integrated these sort of systematic oddball paradigm with some more generalizable rules, where you had, as a patient, you had to distinguish these different states. And they were able to distinguish a conscious part of the P300 from an unconscious part. So can we use these tests where you play different things to the patient to distinguish conscious from unconscious patients? You can also stimulate the brain electrically, so you can do that directly and look at how the EEG signal is processed. This electrically stimulated potential is processed across the brain. You can do that by direct brain stimulation or indirectly by using the vagus nerve stimulus. That is sort of still evolving work. You can also use magnetic stimulation. So you can take basically a specified part of the brain, stimulate this with a magnetic pulse, not with an electrical pulse, and you can see how that's processed across the brain. That allows you to calculate a measure which is called PCI, the perturbation complexity index, that correlates very, very well with patients being conscious or not conscious. What is required, it's not really practical to do that in the ICU setting at this point in time. What is required is to do a high-resolution MRI scan. Then you have your magnetic stimulating device, and you have to find exactly one part of the brain. So what they did in this study, stimulate the bilateral mid-caudal superior frontal gyrus and the superior parietal lobule. And they looked then at how that magnetically induced stimulus was processed across the brain. So very interesting emerging work, but this is basically passively stimulating the brain either with auditory, with electrical, or with magnetic stimulation, and then seeing how that is processed across the brain. Last, I want to talk a bit about work that we've been doing and some others have been doing, where we expose the patient to an active task. So we call it functional motor, we don't call it motor imagery paradigm, but functional motor activation paradigm, where we ask the patient to keep opening and closing their right hand. Then we say, stop opening and closing their right hand. We do this over and over again. Then we do the same on the left hand. We do the same again on the right hand. We go back and forth. And we have basically what we call a block paradigm. So you have one block of keep opening, stop opening, keep opening, stop opening, and you go back and forth over and over again. You record the EEG at the same time. You clip the EEG 10 seconds afterwards and generate 2-second sort of clips of that. You then take all of this EEG and expose it to a power spectral density analysis. So basically, again, as I explained to you before, look at fast and slow frequencies and look at the amplitude in those frequencies. You do that at every electrode and you generate basically a huge data mart of many, many different features. Those features from each electrode are then fed into a support vector machine learning algorithm. That support vector machine learning algorithm learns then what the response is after a move compared to a stop move command. And the classifier then allows you to classify whether the patient systematically responded different to the move command compared to the stop moving command. And those patients that do that then are called cognitive, to be in a cognitive motor dissociation state. So we were able to find that 15% of the patients that looked clinically completely to all extents and purposes, they looked unconscious, actually were in cognitive motor dissociation. So they were not responding to any commands, they didn't move their hand or anything, but when we analyzed the EEG, they had systematically a different response to the move command compared to the stop moving command. What was interesting was that those patients that had the CMD actually recovered, of those that recovered consciousness, 50% recovered consciousness and only a quarter of the non-CMD patients. Interestingly also, those that recovered consciousness, the 50% with CMD, recovered consciousness much earlier than the quarter of the patients without CMD recovered consciousness. So you predict whether somebody does recover consciousness during the hospitalization and also at what time point they recover consciousness. Also good, and most importantly, at 1 year after the injury, you had those patients with CMD had a much higher chance to have a good functional outcome defined as a Glasgow outcome scale is standard of 4 or above. So those patients had a much higher chance to have a good functional outcome. Lastly, I just want to briefly mention brain-computer interfaces. So that allows you to expose the patient to a task. You record what they do while they're trying to do the task. For example, you have a computer screen and they are asked to move the bar up and down. You record a biosignal like the EEG, for example, what they're trying to do. And then you put that into a computer analyzing what the patient is trying to do. Initially, you support their efforts by moving the bar up, for example. And at some point, the patients can actually, with this biofeedback system, they can actually control the computer. So that's called a brain-computer interface. We wanted to see, and this is ongoing work, whether patients in cognitive motor dissociation or unconscious patients can actually do this. We built a brain-computer interface. So this is a trial patient that was completely conscious, so we could assess whether they're conscious. And this was a poor woman that had a spinal cord injury. She couldn't move any part of her body, but she was able to steer a computer just with thinking about how to control the computer. This has been recently also shown to allow you the detection of patients in the chronic disorders of consciousness state with CMD just using these brain-computer interfaces. So there might be some future in using this in more accurate predictions. Confounders are there to consider. You have to think about What are you really analyzing there? What is a representative sample? Would all the EEG be analyzed? Artifacts have to be considered. There are confounders there, like medications, metabolic effects, and the computational analysis has to be standardized. So there's some interesting work going on trying to address that. Here, the Paris group showed that you can downsample the number of electrodes, so you don't need a 256 electrode array. You can downsample to much lower degrees, and you can still detect patients with cognitive motor dissociation. In the resting states, one of the considerations has that consciousness can only be implied. You cannot directly test whether somebody is conscious. The generalizability of the models has to be considered, because if you detect consciousness in one machine using one machine learning algorithm, that doesn't mean you can do it with another cohort. However, having said that, recently the Paris group showed that a machine learning algorithm built to detect cognitive motor dissociation or other behavioral states, just applied to a different data set, was pretty accurate. In the active tasks, we have to consider that artifacts have to be managed with care, and that they may be quite computationally challenging. This is important, as has been shown in this paper by several authors here in the past, where it was shown that muscle artifact, for example, may be falsely be picked up as cognitive motor dissociation. You have to be very conservative when you do this. I want to highlight this paper by Komaduchi, recently in Clinical Neurophysiology, that goes through all of the methods and gives you an idea how to do this. We also published our code with the paper that we published in the New England Journal of Medicine to allow anyone to do these studies. So in summary, there's many electrophysiological approaches available for prognostication and assessment of consciousness. Carefully design algorithms when you choose your analysis plan. And the great summary is the Komaduchi paper. I want to highlight the Curing Coma campaign, an international initiative bringing researchers from all over the world together, trying to address important questions of comatose patients. So please get involved. There's researchers from all over the world involved. So these are people that I work with, my data analysis team here with Kevin Doyle and Qi Shen and others, our research coordinators, Angela Velasquez, who is sort of the director of research operations here in the NeuroICU, many residents and trainees, some external collaborators that I work with closely. And this is the NeuroICU team that I work with, David Rose, Sujin Perk, Sachin Agarwal, and Shivani Ghoshal.